My name is Alan Halakmi. I'm a Director of Solutions Architecture at AWS.
Yeah, good afternoon. My name is Steve Seymour. I am the Solutions Architecture Tech Leader for networking. So this is the AWS Networking Fundamentals session, and as a result, we kind of expect you to have a little bit of understanding of networking in general, and we're hoping to fill in some of the gaps around the AWS networking specific elements. So all of the slides that we're showing you are available on SlideShare after the event, so you can download them from there. But let's kind of jump into this and start perhaps from a long way away. Let's take a distant view and look at the global infrastructure. So this is the AWS Global Infrastructure. The yellow dots on the diagram represent the AWS regions around the world. And the blue lines are the network connections between all of those different regions. And each of those blue lines are actually multiple 100-gig parallel, resilient, and diverse connections between all of our points of presence and our regions on the infrastructure. So I mentioned AWS Regions there. An AWS region is a geographical area. So it is designed to be completely isolated from the other AWS regions, but obviously connected to that backbone with the exception of China. When we look at an AWS region and we translate this into a logical diagram, this is what we're going to be seeing a lot of throughout the session. This is how we represent it, and it's identified by a name, US East 1 in this case. And what that means is that this is a region that is in the US. It's on the East Coast, and it happens to be the first one. So US East 1 is the region that we're going to be talking about here. A region is made up of availability zones, and the concept of an availability zone is that they are close enough together that you can do synchronous replication between perhaps databases, et cetera, but they have different risk profiles. So you can build your highly available applications within a region across multiple availability zones. So the availability zone, let's go back to our logical diagram here again. It's represented by the two boxes in the middle of the region that I've shown here, and we identify them by a letter. So now the availability zones in the region, we're looking at US East 1A and US East 1B. Now, inside an availability zone, we have one or more data centers. And inside the data centers, as you would expect, we have multiple racks, and inside those racks, we have lots of hosts. Those hosts are the ones that are running things like your EC2 instances. And go back to our diagram, we can place those EC2 instances now within the availability zones. And it probably now makes a little bit more sense why they're placed there, given that they're in a data center inside an availability zone. Now, this session is about networking. So the next piece we need to add to this diagram is the VPC, Virtual Private Cloud. And VPC is your isolated, logically defined part of the AWS infrastructure that connects all of these pieces together. And it's going to be the core of what we're talking about for the rest of the session. So let's take away the physical infrastructure for a moment and just look at the logical view. And in fact, let's just look at VPC itself, because VPC is the same in all of the AWS regions. A VPC exists within the region, and it covers all of the availability zones within that particular region. Let's go down to the next level of detail. Although we've defined our VPC, we now need to identify where we can place those EC2 instances in my example, and we need to place them inside what we call subnets. And a subnet is aligned to an availability zone. And you can have multiple of them per availability zone here. So I'm showing you 2 subnets per availability zone, or AZ. Those EC2 instances then sit inside that subnet, and that's where they pick up their connectivity to the rest of the subnets in the VPC itself. And actually, that VPC could be a bit of a lonely place if we didn't have any other gateways or any ways of getting in or out of our VPC. So we need to add a few other components to it. So here, for example, I've added an internet gateway at the top, a virtual private gateway at the bottom. On the left, we've got VPC peering connections, and on the right, we've got VPC endpoints. So that's a lot of terminology I've just thrown at you there, and we're going to dive into the detail of each of these and more throughout the session. But as I say, this is intended to be a starting point. It's to give you an idea of the things that you could be using in your VPC and what they provide. And obviously, there's a lot more detail available in other sessions here at reInvent, and obviously available on our website and in our documentation. So when we look at something like this, we probably need a purpose for the rest of the session. So for at least the first piece, what we've decided to do is just build out a very simple example web application hosted on AWS inside a VPC. So this is what we're aiming for towards the end of the first part of the session. Now, inside our VPC again, let's go back to those subnets and just think about how all of the components we're going to put here are going to communicate with each other. And perhaps, obviously, you might be thinking they need IP addresses. So how does IP addressing work inside a virtual private cloud? Well, first of all, you define what's called a CIDR range. Now, a CIDR range identifies a block of IP addresses, and you might have seen the notation before, something like 172.31.0.0/16. What that means is the last 16 bits of that, you can vary those. You can go from 0 to .255 for both of the last pieces of that IP address. And CIDR notation is a way of representing that. You also might have heard of RFC 1918, and that's the document on the right-hand side of the screen here. This is actually a pretty old document, but it is a document that defines blocks of IP addresses that are intended for use on private networks. So these IP addresses are not routed publicly out on the internet. If you placed a packet out there, it would get dropped by the various internet providers out there. It's intended for use within those private networks. And it may look familiar. 192.168 is pretty common to use for home broadband connections, for example. So this document defines RFC 1918. And at the bottom here, I've identified how much IP address space should we choose. So a /16 is the largest address space that you can allocate to a VPC as a single CIDR range. So that's about 65,000 IP addresses. The smallest you can assign is a /28, which is 16 IP addresses. And actually, the smallest that you can assign here is probably not something you would ever do, because that is also the smallest amount of IP addresses you can assign to a particular subnet inside the VPC. So if you only had a /28 for the whole VPC, by definition, you're in one subnet, which is in one availability zone, which is really not a well-architected pattern that we're going to see there. We want to be spread across multiple availability zones for our infrastructure. OK, so where do these fit back on our diagram? Well, first of all, let's put that main CIDR range on the VPC itself. So the VPC we're working with is 172.31/16. And now we can divide that up into smaller amounts of address space to assign to each of the subnets inside the VPC. So let's take our first one on the top left. This is 172.31.0.0/24. So this is a bit more of a familiar subnet mask that you might have seen. This is 255.255.255.0. That's a /24. And we're going to assign .1 to this other subnet. The other two at the bottom here, I'm going to do something a little bit different. I'm going to assign .128 and .129. And the reason for that will become a little bit clearer later on, but generally what this means is I can identify that group of subnets at the top just by one single CIDR range, and perhaps use them in other places in my VPC in things like security groups, network ACLs, etc. Now, what about IPv6? So as you can see here, IPv6 has a few more bits to its address, takes up a lot more space on slides. One thing we need to look at here, there are a couple of different types of IPv6 address. So we have a unicast addressed, and we also have multicast going on here. There's also things like linked local addresses and a couple of other concepts. But the thing that we want to focus on out of all of this is the unicast address. So let's think about how we're going to use this on our VPC. If you choose to use IPv6, you don't actually make a choice on the v6 range of addresses that you're going to use. You choose to enable it on your VPC, and AWS will assign you a /56 of IPv6 address space. It's part of our address space, and we assign it to your VPC. When you're assigning to the subnets, although you can choose which pieces of that to assign to the subnets, it has to be a /64. And that's because this is plenty of IP address space for everything that you would do inside that VPC. Now, what this means is your VPC is now running in what we call dual stack mode. That means an EC2 instance or any other resource inside your VPC that supports IPv6 will actually receive both an IPv4 address from that private address space we defined, but also an IPv6 address. So just as an example here, this is the output from an IF config on a Linux instance running inside a VPC. You can see the IPv4 address on there, the 172.31. But underneath that, you can see something that's called the linked local address for IPv6. And what that means is that's an address that can be used to communicate with other instances just within the subnet. After that, we have the global unicast address, and this is the address that is basically publicly routed on the internet. It's part of what we assigned you for your VPC, and we're going to explain how you can allow that traffic to flow or allow it to flow in one direction and not others slightly later on. So let's go back to our VPC and place those addresses on the VPC for the complete picture. So we've got the /56 that has been assigned by AWS to the VPC. We're also then going to start assigning those 64s, those /64s, to each of the subnets. So here we are. I've aligned the numbering to be similar. Makes it a little bit easier just visually and to work with. So we're going to assign those /64s to each of the subnets. Now, In terms of IPv4, I do just want to touch on the fact that I mentioned that this is the single CIDR range that you assign to your VPC. You can actually assign more /16s to your VPC if you need more IP address space.
So we're building our example web app, and we actually want internet traffic to interact with our web servers. So there are 5 things that we need to have be true in order for that internet traffic to interact with those web servers. Those 5 things are having a public IP address, having an internet gateway attached to the VPC, having a route to that internet gateway, allowing the traffic through our network access control lists, and allowing that traffic through our security groups. We'll go through each of these and provide some context along the way. So you saw Steve articulate what a VPC looks like when you allocate IP addresses. Let's start with IPv6. As you saw in the screenshot that Steve provided, for IPv6, your Linux instance, for example, will receive a global unicast address, a publicly routable IPv6 address. That IPv6 address is from AWS's address space, but it can be assigned to the instance or to the VPC resource in 2 ways. One is that you can specify the particular IPv6 address within the CIDR range that AWS has defined. That is the opportunity in the EC2 console during execution to specify it. The other option is an auto-assigned IP address. Auto-assigned IP address means that AWS will randomly assign an IPv6 address to that resource at the time of launch, obviously within the context of that IPv6 CIDR range. In the case of IPv4, you saw Steve provided internal RFC 1918 private IP addresses. So how do we get a public IP address? Well, you have a couple of options. For the private addresses that are on your EC2 instances, you can also manually assign them. You can also have them auto-assigned by AWS as you launch. But what about the public component? Well, the same is true of the public component. You can either have AWS provide you an auto-assigned public IPv4 address that maps to the private IP address, or you can pre-allocate an IPv4 address either from AWS's public IP address range or from an address range that you bring to AWS using our Bring Your Own IPv4 feature. So let's take a look at what that looks like now. Go back to our diagram. Just looking at IPv4 for the moment, our web servers on the top in the public subnets. These have internal private IP addresses, and they have these public IPv4 addresses. How does this translation between the internal IPv4 and the external IPv4 address occur? Obviously, as Steve mentioned, that 172 address will not route on the internet. We need to use these 54 or 52 dot addresses. This gets us to the notion of gateways, endpoints, and peering, and we'll have a lot to say about this during the course of the presentation. But for the moment, let's focus on the internet gateway. The internet gateway provides a mechanism for your VPC to connect to the internet. It also provides, in the case of IPv4, stateless one-to-one NAT between the internal IP address that's assigned to your EC2 instance and the public IPv4 address that has been assigned. So what does this actually mean? Well, go back to our 5 things. We've talked about a public IP address, and we've talked about how the internet gateway will allow you to provide that one-to-one NAT in the case of IPv4, or in the case of IPv6, you've directly assigned that to your EC2 instance. To create an internet gateway, on the left side is a screenshot. You click Internet Gateway, you attach it to your VPC. We've actually now met condition 2. So we have a public IP address, we have an internet gateway, and it's connected or attached to our VPC. The third thing that we need to do is we need to have a route to that internet gateway in our route table, right? So in the case of AWS, we think about route tables as the component that is associated with a subnet that defines next hop routing behaviors for packets emanating from that subnet. So here I have a sample route table. It has 4 entries. The first 2 entries say, if this is 172.31, that's part of my local VPC. There is no next hop. It's available through the implicit router that is on the subnet. Same with IPv6. If it's part of this /56 CIDR range for the VPC, there is no next hop. Just use the implicit router, and the instance will be able to get to other instances in the VPC. The last 2 lines here demonstrate what a default route looks like in a route table. So you have the 0.0.0/0. That's an IPv4 default route, pointing in this case to an internet gateway. And below that, :/0, the IPv6 route to the internet gateway. Right? So we have our public IP address, we have an internet gateway that's attached to our VPC, and we have a route table with a route to that internet gateway. It's worth mentioning that oftentimes you have a desire for your resources in your VPC to connect out to the internet, but you don't want anything that originates from the internet to come into your VPC. In the case of IPv6, we use something called an egress-only internet gateway. And as the name implies, it allows IPv6 traffic originating from inside of your VPC to egress to the internet. However, traffic originating from the internet does not have a path into the VPC. And this is semantically similar to something we'll talk about in just a couple of slides called NAT Gateway, which is relevant for IPv4. Now, I mentioned public subnet just a moment ago. And you've seen the private subnets, at least the blue coloring here, in some of the slides that we've put up already. The difference between a public subnet and a private subnet is solely that the public subnet is associated with a route table that has a route to an internet gateway. It is a shorthand that we use in AWS to articulate whether the subnet that is being used has a path to the internet gateway. So you can see here in the subnet, in the route table associated with the public subnet, last two lines, there is a route to the internet gateway. However, in the private subnet, there are only routes to the local VPC CIDR ranges. Okay, let's look at this in practice. What does that actually mean? So on the left side, instance A is in a private subnet. You can see the subnet route table below it. On the left side, the private subnet. On the right side, you can see the public subnet and the route table associated with it below. Again, the public subnet associated to a route table with routes to internet gateways. What this means is that instance A on the left and instance B on the right have a path to communicate between one another. They both have routes to that local VPC CIDR. However, instance B on the right side also has a route table with routes to the internet, meaning that instance B has a path to the internet. Well, what happens when instance A needs to download a patch from the internet? How would that work? Well, that's where the NAT Gateway comes in. NAT Gateway is a managed service provided by AWS that provides port address translation, allowing instances and resources in your private subnets to gain access to the internet. So we've made a slight modification to the route table on the left side that's associated with the private subnet, and it now has a default route entry that points to the NAT Gateway. The NAT Gateway in turn sits in the public subnet on the right side. That public subnet obviously has a route to an internet gateway. In practice, a packet emanates from instance A. It's received by the NAT Gateway in the public subnet. That packet has its IP address, the source IP address, changed to the internal IP address of the NAT Gateway. The packet's forwarded on to the internet gateway, at which point a one-to-one NAT occurs between the NAT Gateway's internal IP address and the elastic IPv4 address that you see here. As the packet goes out to the internet, traffic from instance A is seen to have been coming from that public IP address. All right, so we've met three of our things so far, of the 5 things that we need to do for bidirectional traffic. We have a public IP address, we have an internet gateway attached to a VPC, and we have a route table that has a route to an internet gateway. The last 2 items are really around network security. And as we talk about network security, we're also going to care about the flow of traffic inside the VPC. So we'll talk about VPC flow logs and traffic mirroring as well, but first let's finish out our 5 things. Thing number 4 is network access control lists. Network access control lists wrap subnets within your VPC and define the allowable flow of traffic. Network access control lists are stateless. You can provide allow and deny statements, and those statements are evaluated in a set order that you define. By default, Amazon provides you a network access control list that allows all traffic inbound and all traffic outbound. So what does this look like in this particular example? As we're building out our application, a client on the internet wants to access the web server on HTTPS, so 443 TCP. What would the network access control list look like to allow that? Well, in this case, we can just use the default. So here you can see I'm allowing all protocols, all port ranges from any source to come into my public subnet. And because this is stateless, I also need to define an outbound network access control list, and we'll just mirror. All protocols, all port ranges to any destination is allowed. This is the default configuration, and it's the default configuration that is used by the vast majority of our customers. But what would it look like if we wanted to actually lock this down a little further? Well, the web server is going to talk to the app server. The app server is listening on TCP 8443. So our web server wants to initiate a connection from its source port 6000 towards the application server's TCP 8443. What would that network access control list look like? So here we've defined an allow statement. So traffic targeting port 8443 from a source site range that defines the public subnet range. This is what Steve was talking about before in terms of being able to define in a singular site range the block of IP addresses that were in the public subnet. That is allowed. Okay, so the traffic can make its way from the web server, its source port of 6000, towards the app server. What about the return traffic? Well, we need to define that as well. Again, this is a stateless firewall. So here, a custom rule that allows TCP traffic to return to the public subnet, provided that it is originating from a port of above 1023, destined for a port above 1023. So that's the network access control list. Again, the default configuration for the vast majority of our customers is sufficient. Now let's go to the last of our 5 things, the security group. The security group is the thing that, if you get this right, you are the vast majority of the way towards securing your network on VPC. Security groups operate with allow statements and provide a stateful firewall that sits around the network interfaces of the resources in your VPC. So we call these elastic network interfaces, or ENIs. So here again, we have our client on the internet. They want to get to the web server. I've defined a security group that is attached to these web servers. If I look at the security group, the way the definition is set, inbound 443 on TCP from any source address is allowed, right? These are coming from the internet. So that works. The traffic now gets to the web server. The web server, in turn, is going to make a connection to the app server on port 8443. So if I look at the security group configuration, and again, these are inbound configurations, no outbound configuration is required because this is a stateful firewall. You note that the app server has this source here. Well, 8443 is allowed from this SG. Well, if you look, that SG is the security group identifier for the web server security group. Why does that matter? Well, if you're designing a well-architected infrastructure, in this case for web servers, you're going to use autoscaling to automatically expand and contract your capacity. And as you do that, you want the app servers to dynamically allow traffic from these new IP addresses that are appearing in the public subnet. You may have other things in the public subnet, however, that should not reach the app server. By making a reference in the security group for the app servers that references the security group for the web servers, as these new instances spin up, AWS automatically resolves those IP addresses such that the traffic is allowed through. So we've talked about this ability to have traffic come inbound, and we've also talked about security groups in the context of CIDRs in the web server case, and in the context of security group references in the app server case. What about outbound security groups? Well, by default, AWS allows no inbound traffic, so we've had to allow it here. But by default, AWS allows all outbound traffic in a security group. But you can also lock down the outbound flows through a security group as well. Here, what I've said is I want the application servers to be able to go out to the internet, provided that they have a specific destination. And here you see this PL dash. PL is a prefix list. I can use the AWS command line interface to describe the prefix list. And I see the set of IP addresses associated with the prefix list. And further, I can see that this is the S3 service in US West 2. So what this security group says is that these instances can communicate with the internet, provided that the traffic is heading towards S3 in US West 2. Again, because this is a stateful firewall, no inbound rules are required. And of course, these rules apply based on the target IP address. So whether you are in a public subnet going directly out to the internet, or you're in the private subnet going through a NAT gateway on the way out, the rule applies the same. So we've met our 5 things: public IP address, internet gateway attached to a VPC, route to the internet gateway, the network access control lists allow the traffic, the security group allows the traffic, Now we have bidirectional communication with the internet. So packets are moving around in the VPC. Let's get some visibility into what's happening in that VPC. VPC Flow logs provides IP fix or NetFlow-like data that is available to you either through CloudWatch logs or Amazon S3. On the right side, you see a set of the data elements that are available through the service. A key point with VPC Flow logs is that it does not impact the bandwidth, throughput, or latency of the network interfaces in your VPC. You can apply this monitoring to your VPC, to a subnet, or to a specific network interface. But what if you wanted to get the actual packets? Not just the flow information. You want to capture actual packets. Maybe you need to do inspection. Maybe you want to do analysis. That is available to you with the Amazon VPC Traffic Mirroring capability. Traffic mirroring allows you to identify a source and a target, and those two, a source interface and a target that will receive the packets. The thing to know about the VPC traffic mirroring is that because we are doing packet copies within our Nitro architecture, you are sharing the bandwidth of that network interface with the traffic that is being exchanged in your VPC, right? So if you have a network interface on an EC2 instance, you are sharing the bandwidth of that network interface in order to use traffic mirroring. To use traffic mirroring, you set up a traffic mirroring session, 3 components, the source network interface. You define the interesting traffic using something called a filter, where you specify the particular components of interest when we should be capturing the packets. And of course, you define the target for the traffic flow. That target can be another network interface, or it can be a network load balancer with a UDP listener. Now, we should probably talk about load balancing. So we showed you our example web application. We had EC2 instances. In reality, you actually probably won't have EC2 instances sitting directly on the internet. Think about auto-scaling. As you start adding instances or contracting the capacity that you're providing, you don't really want to rely on DNS, right? There are many resolvers out there that do not honor time to live. So in the worst case, you could have contracted capacity and traffic is still flowing towards an IP address that no longer exists. That's a bad customer experience. So instead of having traffic flow directly to the web servers, we can put in elastic load balancing load balancers from AWS to help distribute traffic. ELB, or elastic load balancing, provided by AWS comes in 3 varieties. We have the application load balancer. This is for HTTP and HTTPS type traffic. We have the network load balancer, which supports UDP, TCP, and TLS offload. And we have a third type of load balancer that I've conspicuously put in gray. If you have an account that was created after 2014, you do not need to worry about the third type of load balancer, which is called the classic load balancer. And if you haven't noticed, anything that we call classic is an indication that you probably shouldn't use it. So for our load balancers, we have different types of endpoints that we can load balance traffic to, EC2 instances, containers, Lambda functions, or other target IP addresses. So while we won't have time to get into the specifics of load balancing here, I do want to just leave you today with information about what the overall anatomy looks like. So for ALB, the first thing that we have to have, both for ALB and NLB, is a listener. And this is the port and protocol on which that load balancer is listening. So for our sample web application, that's going to be TCP 443. For each listener, we can define rules. In this case, with ALB, I've defined path-based rules. So if the path is /img/star, I want the traffic to take a flow to a particular target IP address. Otherwise, I'd like the traffic to flow to my web servers. These listener rules identify target groups where they pass the traffic, and the target groups contain targets. So we've built our web application. We have our elastic load balancing load balancer there now. Internet gateway, traffic comes in, ELB, web servers, and app server. Now, of course, since we have our ELB and it now has the public IP addresses, we don't really want or need public IP addresses on our web servers. So from a well-architected perspective, if it doesn't need to be on the internet, it shouldn't be. So we're going to take our web servers, pull them into private subnets, exposing only our elastic load balancer.
OK, so we've got our application running in our VPC, but it's quite common to actually have multiple VPCs within your architecture. So how do we connect these VPCs together? Now, we've taken 3 example VPCs here. And of course, one of the things that we could do is just put an internet gateway on each of them, put public IP addresses on our instances, and then communicate over the public internet. That would work absolutely fine. However, you may not actually need these VPCs to be public on the internet. You may not need the instances to have public IP addresses at all. And that's where VPC peering fits in. So instead, let's take away the internet gateways and establish this private connectivity across the AWS infrastructure between our VPCs. How do we do that? It's really quite simple, actually. You go onto the console here. You could do this, of course, via the command line or via our APIs as well. But you simply just identify which VPC you want to connect from and the VPC that you want to connect to. Now, VPC peering can work both within the same AWS region or across regions. It can also work within the same AWS account and across different accounts. So depending on how you've deployed your application, you can make the right decision of which type of peering connection you want to create. So let's look at peering within the same region first. So we just need to enter the VPC ID for the VPC we want to peer with here. And then when we go back and look at our connectivity, we now have a peering connection. But there is one more step that you have to complete. It doesn't matter whether that peering connection is to a VPC in the same account, same region, or different. You have to actually accept that peering connection. Now, once that's done, we have a path to be able to send traffic over between these two VPCs. But as you've probably got the idea now, not much interesting things happen inside a VPC until you put an entry in a route table. So what we actually need to do here is take a look at our route table and specify that for traffic to get to the IP address space, the CIDR range of the other VPC, we put an entry in that route table that says, to get to that range of IP addresses, go via the peering connection, the PCX identifier. Now, we need to do that on both ends of the peering connection because otherwise traffic would be able to flow in one direction, but it wouldn't know how to get back. So we've now peered these two VPCs together. And what if we wanted to add a third one into the arrangement here? Well, you just repeat that process. So we just build a peering connection between the other two here. We go in, and again, we need to modify the route tables. So now we have two entries in our route table here that says to get to one range of IP addresses, go via this peering connection, and to get to the other range, go via the other. And as I said a moment ago, you obviously need to repeat that for each of these VPCs and add those entries into the route tables. So at this point, all three of our VPCs have a path to each other. Now, you might ask, do we actually need to create all of these peering connections here? Because the VPC at the bottom has a connection to the VPC on the top left. Top left has a connection to top right. Surely there's a path there for traffic to flow. And actually the answer is no, that doesn't work. That would be called transitive routing, and that would mean that you are passing through the VPC on the top left. So actually, if you don't have a peering connection on the right-hand side of this screen, that traffic will not flow. Now, I mentioned that you can peer within the same region or across different regions. What's the experience for that? Let's go back to the console again. It's that same screen that we were looking at before. But you'll notice that there's a slightly different option to choose at the bottom here. We simply choose the other AWS region from the dropdown, specify the VPC identifier, and then the process is the same. Equally, if you're peering across accounts, you just need to specify the AWS account number for the other VPC. And again, this could still be across region or in the same region, so any combination of those. A couple of things just to remember about VPC peering when you're connecting your VPCs together using this. First of all, the security groups that Alan talked about a moment ago, you can actually reference those between VPCs in the same region if they are peered. So you can specify the security group identifier in another security group as the source of traffic, and that works across those VPCs when they're peered within the same region. You can enable DNS hostname resolution between those peered VPCs. What that means is that when you turn on DNS inside your VPC, and we're going to show you that a little bit later on, it means that you can resolve the public DNS names for an instance inside the other VPC, and our service will actually resolve them to the private IP address because a path exists across that peering connection. When you're peering VPCs, you compare the IPv4 and the IPv6 addresses. But a couple of things to look out for. You might have noticed on that previous slide that the IP address space I was using for each of those VPCs was different, and that's because you cannot peer VPCs together that have an overlapping IP address space. So think wisely about the IP addresses that you assign to your VPC, whether you're going to choose them from that RFC 1918 ranges or from another block of IP addresses that you're choosing to use within your virtual private cloud. You can't peer two VPCs together multiple times. You only create a single peering connection between those two VPCs. And from a jumbo frames perspective, this is supported across VPC peering. This is not supported across VPC peering when you're going across regions. It's supported within the same region. Okay, so we've connected our VPCs together. Our architecture's starting to grow here. What if we need to connect back to perhaps some on-premises infrastructure or an existing data center of some sort? So now we need to adjust our diagrams a little bit here. We've got another component to add in. So we have our VPC on the left. It's now using the 10/16 address space. And on the right-hand side, we've got our corporate data center. This is what we want to connect back to. And there are a couple of ways of doing that. We're going to start by looking at site-to-site VPN. So this is a standard IPsec-based VPN. And for any type of VPN connection that's going over the internet, there needs to be two ends to it. So first of all, let's define the AWS side of this site-to-site VPN connection. And here we use something called the virtual private gateway. And the clue is in the name private there. It's connecting to private networks. It's connecting to your virtual private cloud. And we need to define that first. And we do that quite simply by clicking the button in the console and choosing what is called the AS number for this. So this is the autonomous system number. It just identifies the network on the AWS side. And you can just use our default for that, or you can choose your own if that is relevant to your infrastructure. Now, once you've done that, we actually need to look at the other end of this site-to-site VPN connection. And this is the infrastructure that exists within your network. So you have to tell us about that. You have to identify it, and we call that the customer gateway, or CGW. And once again, in the console, you choose to create a CGW and gives a bit of information about it. Now, this is the point where you have to start thinking about the type of site-to-site VPN connection. Is it going to be static or dynamic? What that means is if it's static, you have to identify the IP address ranges on each end in advance. If it's dynamic, then you can use a routing protocol, in this case BGP, to exchange that routing information from both sides so they will learn paths to each other automatically. Again, you have to assign an AS number to identify your network. There's a range of private AS numbers here that you can just use. And you also need to identify where that customer gateway is out on the internet. So where is it connected on your side to the internet? What is its IP address? There are some occasions, though, where you may not have a fixed IP address for that customer gateway. And what's really useful here is that we support certificate-based VPNs. So we can identify the connecting customer gateway here using a certificate, and in which case you don't have to specify the IP address for it. So let's go back to our diagram here and now complete the connection between these two ends. Well, this is really simple. In the console, again, there's a button that says Create VPN Connection. And when you do this, we automatically provision two endpoints on the AWS side. These are in two different availability zones for the region. And the next stage is then simply to connect those two endpoints back to your customer gateway. So at this stage, we have a single VPN connection. But to AWS, what this means is that it is two tunnels. And that's because we want this VPN connection to be highly available for you. You can obviously scale that up as well and add additional infrastructure on your side and build multiple VPNs if needed. So let's go back and think about how we're going to route across this connection. We're using dynamic routing here, so we're using BGP, which means the virtual private gateway has now learned about your data center's infrastructure, the 172.16 range. But actually, what about your EC2 instance? Your EC2 instance is sitting in a subnet with a route table, but it doesn't actually know how to get to the on-premises network. So what do we do here? Well, we go to that route table, and we add an entry to it. So we put 172.16/16 into the route table with a next hop, a target of the virtual private gateway. So now we have the ability to pass traffic end to end. One other thing I did just want to call out about this type of VPN connection to the virtual private gateway is each of those tunnels is 1.25 gig per second. Now, from an AWS perspective, when we send traffic to you, we actually treat these as a failover pair. And that means that we use one of these paths as the primary. So when you're using a site-to-site VPN with the virtual private gateway, the maximum bandwidth on that VPN connection is 1.25 gig per second. So an IPsec VPN, a site-to-site VPN, goes over the internet. It could be subject to what are generally termed things like internet weather events, so perhaps variable latency out on the internet. There are other options here if you needed to have a more consistent experience and you wanted to connect directly to the AWS infrastructure. And this is something called AWS Direct Connect. AWS Direct Connect has a couple of components to it. So it has the physical connection. This is a 1 or a 10 gig connection directly into a router that is owned by AWS. And these routers are hosted in Direct Connect locations. These are typically colo locations all around the world where you actually may have your own infrastructure. So in the example that we have here, we're actually showing that you perhaps have a customer router in that data center and your infrastructure behind it back in your offices and your other locations. So that's the physical piece. You have established your connection to one of our many Direct Connect locations around the world. But how do you configure the logical connectivity on top of that? Well, this is where we step into something that are called virtual interfaces, or VIFs. And there are three types of virtual interface. The first one is private. And the way to remember this is, again, you're connecting to your VPC, virtual private cloud. You're probably going to be needing to use a private VIF. A transit VIF, if you're going to be using a transit gateway, which we're going to show you in a moment, this is where you might need to connect perhaps hundreds or thousands of VPCs. Well, you might need to use a transit VIF to do that. And then finally, a public VIF. A public VIF gives you access to all of the AWS services that are available on our public IP addresses and that don't actually live inside your VPC. So let's put a couple of these pieces back together on our diagram. So we have our physical connection in place, and now we have the AWS Global Infrastructure. And very deliberately here, I have two different AWS regions. I have a couple of VPCs in one of them, and I have a VPC in another one. And we want to connect these together. So as I mentioned earlier, this is going to be a private virtual interface. And we're going to create that virtual interface, which is just a VLAN and a BGP session across that physical connection. And we're going to terminate that on something called the Direct Connect Gateway. And the Direct Connect Gateway is just a logical object. It's not a single piece of infrastructure. But the key thing is it enables you to get from that Direct Connect location, wherever it is in the world, to any of the AWS regions where your resources might be living, with the exception of China. So now you can connect to the Direct Connect Gateway. We then attach the virtual private gateway, the VGW, to that Direct Connect Gateway. And you can attach up to 10 of these across all of the regions. Now, we need to go back to my favorite topic here of routes. How does the VPC learn about these routes? Because earlier we looked at the Sitetosite VPN, we had to put an entry into the route table manually. Well, that could be something that takes a bit of extra admin, a bit of extra work if your network changes. We actually have an option on the route table called propagation. And what propagation does is it takes anything that the VGW knows about, that it's learned over BGP, and installs it into the route tables for you. So turning on propagation gives you an entry like this at the bottom, and you can see that it's got the propagated flag on it. So generally, most customers will turn on route propagation. Now let's just briefly talk about public VIFs. So I mentioned that this is the third type of virtual interface. We're going to come back to the transit VIF in a moment. But the public virtual interface means that the rest of the services on the AWS infrastructure, on the global network, that have public IP addresses, things like S3, CloudWatch, DynamoDB, these are all services you may want to access from on-premises without going through a VPC. So with a public VIF, what we do is we advertise to you all of our public IP addresses for the global infrastructure. So about 3,500 prefixes at the moment, which means you now have a direct path to reach all of those public IPs from your network. Now, I've mentioned transit gateways and transit VIFs a couple of times, so let's fill in the gap around that. You might remember this diagram from earlier when we talked about VPC peering, and we quite simply connected 3 VPCs together. This is very manageable. You simply create those peering connections and establish the routing. But what if your infrastructure grows and you have a few more VPCs? And you could keep growing beyond this, of course, as well. And to enable all of these VPCs to communicate with each other, that is a lot of peering connections to manage and configure. So we introduced something called AWS Transit Gateway. And Transit Gateway simplifies this significantly. So it sits in the middle of the VPCs, and it attaches to each of them. And as this implies here, you now have the option to route traffic via that transit gateway. So let's put that into practice and also use it to connect back to our corporate data center. So let's attach each of the VPCs to it. Now, inside the transit gateway, we actually have the option to do quite complex and quite advanced routing. But for the simplification in this session, we're just going to use the standard default setup, which is a single route table inside the transit gateway, enabling everything to communicate with everything else that is attached. Remember the site-to-site VPN that we talked about to the VGW? Well, actually, we use site-to-site VPN with transit gateway as well. It works in exactly the same way. You define the customer gateway, you create the VPN connection, it creates 2 tunnels to the transit gateway. Back to my old favorite again, let's think about the routing here. We need to put entries in the route table in the VPC to say now, to get to the on-premises infrastructure, send that traffic to the transit gateway. The transit gateway has learned that route over the VPN connection because it was dynamic, and now we have traffic flow end-to-end. How does that work with Direct Connect? Just to close this out. So with Direct Connect, we have the physical connection again and our same VPCs. You can obviously imagine this scaled up a bit more because Transit Gateway can support kind of up to the hundreds and thousands of attachments to VPCs. But in this case, we create a transit VIF. The transit VIF attaches once again to a Direct Connect gateway, But this time, the Direct Connect gateway attaches to a transit gateway. That now allows you to connect to multiple VPCs within that region from that transit gateway.
So we've talked a lot about connectivity, and most of our customers make heavy use of domain name services, particularly those that are using IPv6. So we should talk about DNS because it's relevant to VPC, and we provide something called the Amazon Route 53 Resolver to deliver DNS service to your VPC. A couple of things to know about Route 53 Resolver. First is that the resolver sits at the VPC CIDR +2, or the base address +2 address. What that means is if your address is a /24, for example, it would be at the .2 address. If it's a /25, it could be at the .2 or perhaps the .130 address. So base +2. There's the ability to enable and disable it. We'll talk about that and some DNS hostname support for EC2. And we'll also talk about private hosted zones and the ability to integrate with your on-premises DNS infrastructure. So if you look at your VPC DNS options, you'll find that you have two very specific ones called out. One is for DNS resolution. This determines whether or not the Route 53 resolver is enabled. When this is set to yes or true, that .2 address will be available to you to resolve both private hosted zones and public DNS names. When set to false or no, it simply is unresponsive. It will not respond. We also have the notion of DNS hostnames. DNS hostnames allows EC2, or allows AWS to create for EC2 instances fully qualified domain names. Why is that material? Well, as Steve mentioned before, you're likely going to have instances that are exposed to the internet. You're going to have fully qualified domain names associated with EC2 instances, and they're going to have public IP addresses. Well, you want to use that fully qualified domain name inside the VPC. When you use it inside the VPC, you don't want the public IP address, you want the private IP address. But when that fully qualified domain name is used outside of the VPC by your customers on the internet, you want them to get the public IP address. This capability, DNS hostnames, gives you that capability as well. Steve also mentioned that when this is enabled for cases where you have VPC peering, the same is true. In a peered VPC, the fully qualified domain name that's associated with an EC2 instance will return the private IP address, allowing your resources to communicate over the VPC peer, as opposed to going out an internet gateway and coming back in another internet gateway using a public IP address. So fair enough. We talked about the ability to resolve public DNS names. Route 53 also provides you the ability to resolve private DNS names and DNS names that you define using private hosted zones. Using private hosted zones, you can define these domain names within Route 53, and you can associate them with your VPC. So now the VPC on the left side has the ability to resolve this private hosted zone, example.aws. But I also want the VPC on the right-hand side to be able to resolve that same private hosted zone. So how do I do that? Well, in Route 53, if it is in the same AWS account, regardless of region, you can simply add the VPCs that you would like to use that private hosted zone. If you'd like to associate that private hosted zone with other VPCs outside of your account, that's also possible, but you'll need to use the command line interface to do that. So we've associated example.aws with the VPC on the right, and now when an instance queries the Route 53 resolver for that private hosted zone, it is able to resolve information from that zone. Of course, I can create as many of these as I want. I can share it back the other direction. And so we've used private hosted zones to create the internal DNS names that are needed for our operation. Of course, now that they exist in AWS, I'm going to have corporate users in my corporate infrastructure that will need access. How does that work? AWS has a capability that we describe, or we call, Route 53 resolver endpoints. Resolver endpoints come in two forms: inbound endpoints and outbound endpoints. One to integrate for inbound DNS requests from your corporate infrastructure, and one to make requests of your corporate infrastructure. So we'll go through the two of them. So we have our VPC on the left-hand side. We have our corporate data center. How would we go about integrating for this example.aws private hosted zone, right? Somebody sitting in the corporate infrastructure, they want to resolve example.aws. We create this inbound resolver endpoint. Route 53 places a network interface into your VPC. You create a forwarding rule inside your DNS server on your corporate infrastructure, and now As the request is made to your corporate infrastructure, the forwarding rule takes over. The request is then made onwards to the Route 53 inbound resolver endpoint in your VPC and onward through the private hosted zone, returning that private information. So that's the inbound case. What about the outbound case? When I have my EC2 instance that needs to integrate with example.internal that sits in your corporate infrastructure. Well, in that case, the instance will make a request to the Route 53 resolver. We will create a forwarding rule that states example.internal is available through a particular set of IP addresses in my corporate infrastructure, accessible over VPN or Direct Connect. And Route 53 will create an outbound resolver endpoint. That network interface in your VPC will then make an onward query to the DNS server in your corporate infrastructure. There's much more to say about Route 53 and Route 53 resolver endpoints. Please look at the documentation for more information. One data point just for you is that you can share resolver endpoints between different AWS accounts using something called Resource Access Manager. Other things that you should be aware of because they connect into your VPC. Several AWS services actually run in AWS-owned, operated, and managed VPCs. However, we present services to you. So example, in the case of Amazon Relational Database Service, the EC2 instances run in an Amazon VPC. Their primary network interface sits there. That's the interface that we use for management activity and for backup. But of course, you need access to RDS from your VPC. And so to do that, AWS extends elastic network interfaces into your VPC using the IP address range in the CIDR block that you've defined for your subnets. And that is your entry point into that service. Similarly, if you're using Amazon Workspaces, you download the Workspaces client, you log in, the client connects with the streaming gateways provided by the Workspaces service. They sit in an Amazon VPC. The traffic, that streaming gateway connects you with your virtual desktop sitting on an Amazon EC2 instance, also in that Amazon VPC. And we, as we did before, project an interface into your Amazon VPC with IP addresses from your CIDR range, providing access from that virtual desktop into your VPC. Of course, the primary interface sits in an Amazon VPC. That primary interface is providing the bit stream that heads off to your Workspaces client, giving you access. Now, you'll note that I've given you two examples where we have services that are putting network interfaces into your VPC. So when Steve talked earlier about you really need to think about how you plan out your IP address allocation, keep in mind that you may be using AWS services that will be taking IP addresses from your space as you launch them. We made a recent change with Lambda such that customers that use Lambda to access resources in their VPCs do not need to have a network interface per Lambda function or per Lambda invocation. Instead, using a technology that we released recently called VPC to VPC NAT, or V2N, Lambda functions across invocations are able to share elastic network interfaces and a particular set of conditions. In this case, we don't have a propagation of network interfaces in your VPC, right? So they can all use a singular IP address to access, for example, your RDS server. So one final area that we should talk about, and this is very much from a security perspective, is the notion of VPC endpoints. VPC endpoints provide resources within your VPC the ability to access resources provided by AWS and, in some cases, provided by other AWS customers without having to go through an internet gateway. VPC endpoints come in two flavors. They come in gateway endpoints, where we're using route tables and gateways to access services. And they come in interface endpoints, where we're using elastic network interfaces to access these services. So let's take a look at an example of a gateway VPC interface endpoint, or a gateway VPC endpoint. So the instance on the top left in the public subnet wants to access S3. So it's going to make a DNS resolution request for the FQDN, S3, US East 1, and get back a public IP address. Because it's in a public subnet, it has a route to an internet gateway. Packets go out and onwards to S3. That works. But I also have instances in my private subnet. They also need to get to S3. How does that work? Well, as we talked about before, they can use NAT Gateway, and the NAT Gateway will provide a path through the internet gateway onwards to S3, again, using the public IP address. But what happens if I don't have an internet gateway? How do I access S3 if I'm not comfortable or I don't need an internet gateway in my VPC? Well, in this case, we use gateway VPC endpoints. And you'll recall prefix lists from our earlier conversation about security groups. Well, I can actually put a prefix list in my route table as well. So I can create a gateway VPC endpoint for for S3. I can define that prefix list that describes S3 with a next hop of that gateway VPC endpoint that I've defined for S3. As a result, when the request is made to DNS, I'm still receiving that public IP address, which is contained in that prefix list, with a next hop pointing to my VPC endpoint. The traffic flows to Amazon S3. Gateway endpoints are only available for Amazon S3 and for DynamoDB. The other type of endpoint is called an interface endpoint, where we use network interfaces. In that case, here we have a VPC. It has no internet gateway. I resolve SQS, the public DNS name. I get public IP addresses. Of course, that's not going to work because I have no internet gateway. There's no path. However, using interface VPC endpoints, I'm able to create network interfaces inside my VPC. Behind the scenes, AWS is creating a Route 53 private hosted zone that effectively overlays on top of the same fully qualified domain name that you were using previously. Now, when I do a DNS resolution, I get the private IP addresses that are within my VPC, and I have a path, in this case, off to SQS. Interface endpoints are powered by something called AWS Private Link that's also available to you. In the case of Private Link, we have a consumer-producer relationship. The producer has a network load balancer. That network load balancer is able to send traffic onward to target groups, and consumers receive these projected network interfaces. So here you can see Private Link for your own services. The customer on the left can access the content provided by the producer, on the right. Of course, because network load balancing can support target IPs, those resources could exist in on-premises data centers, allowing customers in AWS through Private Link to access capabilities that you may not have yet migrated into the AWS cloud. Last point about endpoints. Endpoints support something called endpoint policies, which is an identity and access management resource policy. It allows you to do things like, for example, traffic coming through this VPC endpoint to S3 can only pass provided it is going to the data bucket. That's one example of using an endpoint policy. But VPC endpoints can also be referenced in other resource policies. So for example, in S3 on my bucket policy, I could say traffic is only allowed to this bucket provided that it comes from this specific VPC endpoint. Now we've given you a lot of concepts. We're going to try and stitch it together and give you a holistic picture.
So yeah, let's go right the way back to the beginning and take our two availability zones and our VPC spanning them. We created some public subnets with our internet gateway and our elastic load balancing environment here. We created some private subnets with some EC2 instances to act as our web servers, a couple of NAT gateways to provide access out to the internet. We've deployed Route 53 resolver and created private hosted zones to name things inside our VPC. We've perhaps done some VPC peering out to the other VPCs supporting our application. We've created a site-to-site IPsec-based VPN from the virtual private gateway back to our on-premises infrastructure. And we've also deployed gateway or interface VPC endpoints to provide access to other AWS services. Now, we might want to go a step further here, deploy some other services into our VPC, use things like Lambda, perhaps workspaces, RDS, the other examples we've talked about so far throughout this session. In terms of connectivity outside of this environment, we might want to add a few extra things in terms of that corporate data center. So let's deploy a transit gateway, connect to other VPCs and that data center. We can use the other site-to-site VPN variation here to build that connectivity, or in fact, put Direct Connect in place and attach to transit gateways in other regions.
Of course, at AWS, security is our top priority, so we should talk about the security components as well and bring that together. First, make sure you're using a multi-availability zone architecture, right? Multiple AZs. Use the internet gateway and elastic load balancing to provide access, and with security groups, control the flow of traffic through your infrastructure. Make use of NAT Gateway and egress-only internet gateways when you need to be able to get out to the internet, but things should not be coming in. VPC endpoint policies allow you to control access and ensure that traffic is able to access AWS resources without the need to go through the internet. Peering for network connectivity with the ability to be very specific about the ability to speak between particular instances and subnets. Transit Gateway for advanced architectures like bump in the wire. Private link, when you need to expose an application and you don't need network-to-network connectivity. Visibility through VPC Flow logs, and packet capture with traffic mirroring.
So there's been a couple of other sessions this week that obviously give you a lot more detail around these topics. They're all going to be available on YouTube. There's still a couple to go. If you're interested in the physical infrastructure that supports VPC, you might want to go along to the innovation and operation of the AWS Global Network Infrastructure later today. Also, if this has kind of teased you with the idea of learning more about AWS networking, there are training materials available and an advanced networking certification that would be great if you wanted to take that. So with that, we'd like to say thank you very much for coming to the session. Please do fill out the session feedback because we adjust this session each year, and that's really important to us. So thank you very much for coming.
Thank you.